Well, I decided to put just some things which we already saw, just to recall the basic notions here. So a proper variety of a field is universally pseudo-trivial. So if the degree is an isomorphism for any field extension, and I hope that in the definition that I gave, I always assume that there is a zero cycle of degree 1. So if not, this one has to assume this. And also that the zero cycles of degree 0, this group is trivial for any field extension. So this is this notion. Then we have also a notion for a proper map, a similar one, which induces an isomorphism on the Char groups. And I put that for a smooth and proper variety, this notion is equivalent to the integral diagonal decomposition. So this we already saw. And here I put the propositions about the specialization, just to recall the numberings, and also the 3 of them. Anyway, we are going to use these propositions today, so we will go back here. So there are 2 local ones and 1 global one. So I think that I will just keep them here. Okay. So, so today we will see the varieties with non-trivial invariants. So this is the 4th, I guess, part. Varieties with non-trivial invariants. So before giving actual examples, I thought it would be useful to speak about another invariant coming from the Galois cohomology here. So, so first, I will speak about more invariants. Which we will denote like this. So, okay. So let's take K field. And X over K, smooth, and say projective, geometrically integral, variety. Then one has a field, which is the field of functions of X, and then one can associate to this field its Galois cohomology groups, right? With some coefficients, which I denote A here. And A could be, for instance, for us, the groups of interest will be a constant group, where N is prime to characteristic of K. Or also twisted roots of unity with the same assumption. Or also, sometimes I will put the groups like this, like our QL, CL. And then the cohomology groups, in this case, are obtained by passing to the limit. So, for example, one can write that HI, a Galois cohomology group of this field, with, say, coefficients infinite, QL mod ZL J. This will be a limit of the similar groups, but with twisted roots of unity, when we look for L to the power n. And the limit here is over n, and again, L is prime to the characteristic 2 of the base field. Well, okay, so, but we will be not interested in these precise groups, but in subgroups of these groups. So what happens is that if for X smooth and projective, if I take a point of codimension 1, so a generic point of an irreducible divisor, so then we have residue maps which goes from these cohomology groups and which ends to the groups, also Galois cohomology groups, where we consider here the residue field, and we twist coefficients by -1. And then one can define the groups we will be actually interested in as follows. So these unramified cohomology groups is an intersection of the kernels of all these maps. Okay, so these are elements in the Galois cohomology group of the field which have no residues. Okay, and this was for a smooth and projective variety, and if X is not smooth, or you don't know the projective model, or not projective, there is still a way to define these groups. Just instead of taking the points of codimension 1, you have to take all the discrete valuations on this field. Okay? So replace these points of codimension 1 with all discrete valuations V of rank 1 and trivial on the base field. Okay. Okay. So what's good about these groups? So let me describe some properties. So first, they're good for our purposes because they are stably rational invariants. And even better, now we are with this CH0 triviality. So if I take a variety which is CH0 universally trivial, so in particular, I just recall stably rational, in particular, X stably rational. Then what? Then these groups are trivial, which means the following. So then all these groups, they actually coincide with the Galois cohomology of the base field, because something which comes from here always is unramified. Okay? And I, at least one. Okay, so this is good news because maybe we can try to compute these groups in some situations if you want to produce a non-stably rational variety. And also the invariance you know, or the invariance we saw in previous lecture, some of them you can recover here. So in particular, if I equals to 1, then you have nothing more but PK group in various cases. So first, as a normified cohomology, you recover just the cohomology of the variety, which is an Tal cohomology. So this is in general. And also, if K is algebraically closed, then you have just the torsion in the Picard group as the unramified cohomology in degree 1 with coefficients mu n. Okay. Then, for I equals to 2, we recover Brauer group. So the Brauer group is precisely the H2 unramified. No assumptions on the field. Okay? And if you remember what I explained at the presentation, this will be useful here. So for I equals to 3, and the field of complex numbers, so by work of Colliot-Hélène and Claire-Voisin, one can relate, so I think that I will just put it in this way, just as a motivation, relate H3 unramified with an abstraction to integral Hodge conjecture in degree, well, for classes of codimension 2. Hodge conjecture for cycles of codimension 2. So I think I will not say here more, just to put it this way. Okay. Well, the point is that sometimes, because of this explicit description, sometimes one can really compute these groups. Okay, so now that's all for this invariance, and I will give you two basic examples with varieties with non-trivial invariants. So here we go. So the first one will be the variety of Artin and Mumford. So example of Artin and Mumford. Okay, so here we will be over C, but actually Q bar works as well. So consider the following data. This is what is one has to consider. So in P2, we take a smooth conic. Which I denote as the conic given by the equation in 3 variables, coordinates of P2. So this equation with alpha of degree 2. Then we pick 2 elliptic curves for r equals 1 and 2, elliptic curves, such that they are special with respect to this, with this conic, such that each is tangent to R, to A, in 3 points. The intersection of E1 and E2, as you guess, it's 9 points, and all these points are different. All these points are distinct. Then, by some arguments on divisors, one can show that there exists homogeneous form, which I denote beta and gamma, homogeneous, of degrees, respectively, 3 and 4. So beta of degree 3 and gamma of degree 4, such that beta square minus 4 alpha and gamma equals to E1, E2. So this is the data you have to take. So once you take these things, here is what happens. Okay, so take Y the following double cover. So the variety Z4 square plus, well, let me write like this. So this will be an equation of a quartic. So it will be a double cover ramified along the quartic. Plus gamma Z0, 0, Z2. Okay. So here we have a quartic equation on the right, and then we have a double cover. So this Y, it is not smooth, but it has only ordinary double points. So we say that Y is a double cover of P3, ramified along a quartic with 10 nodes along a quartic. This 10 turns out to be important with 10 nodes. And then what Artin in Mumford shows that there exists a resolution of singularities, which you can actually obtain just by blowing up these points, in particular a resolution such that the invariant H3, I think that I already mentioned this in the first lecture, the torsion is non-zero. Okay? And it turns out that here also this invariant equals to the Brau group. Or you can also see this as the Brau group of Z in the even 2 torsion here is non-zero. And the reason I put it this way is that actually in the argument by Artin and Manfred, this construction is quite geometric of the non-trivial elements here. But, well, here. But you can also view this via residues, just in the way I define it, and you can find this proof, so of the fact that this group is non-zero in a work by Colliot-Hélène and Oyen-Guren, which is more like algebraic approach. Well, anyway, we have this in variety with this non-trivial invariance. So this will be useful for us. And also, you can view this variety as a conic bundle just by projection to these coordinates. Okay, also view Y as a conic bundle. Over P2 with coordinates these ones. Okay, so let me give you the second family of varieties with non-trivial invariance. So these will be also covers, but slightly different ones. Okay. So this will be a third part. Ramified covers in characteristic 2. So if you like characteristic 2, this is your, well, the favorite case. Ramified covers in characteristic 2. So in this, for this part, it will be after color. Well, so what you consider is the following thing. So we consider K, just to simplify, an algebraically closed field of characteristic 2. Then consider a hypersurface over K, hypersurface, which I will denote by the one defined by the equation J equals to 0 of degree D. Then the proposition is as follows. So proposition 8. If we choose a double cover of such a hypersurface in a general way, so if y to x is a double cover of x, a general one, so, or, yeah, a general. So this cover, we can view it as a normalization in the function field of x of this equation, y squared equals to f, with degree of f equals to 2 times d. So it's important, t here and 2 times d. And also, which is very important, is some assumption on d. So d is at least, so the upper integral part, I don't know how to say this, but the integer which is not smaller than plus 2, the smallest integer which is not smaller than n plus 2 plus 3. And so then what? Then there exists a resolution of singularities, which I will also denote z to y, which is also obtained by blowing up some isolated points, isolated double singular points. So this resolution is obtained by blowing ups, several ones, blowing ups of isolated singular points. Singular, I would say double points. Such that, so here is another invariant, the differential forms. Okay, h0, z, the n-1 is non-zero. Okay. So I think I will not tell more about the reason of this, and I will rather proceed with examples finally of non-stable irrational varieties using these two invariants. Okay. So finally, the fifth part, examples of non-stably irrational varieties. Okay, so I will go there. So the first such examples were produced by Claire Voisin, where she was using the method of the diagonal decomposition in the following context. So first, Claire Voisin. So double covers of P3. Ramified along a quartic again. So you will see. So we can view such a double cover as a subvariety of a weighted projective space, which we define by this similar equation. So that's the point. So minus F4, where F4 is of degree 4, as one can guess, right? Homogeneous. So you see that as an example of such a variety, we have a singular variety, which is an example of Martin-Mumford, which has 10 nodes. Okay, and what she proves is the following thing. So theorem 1. Let X tilde be a desingularization of a very general, such a double cover, a very general double cover of P3 ramified along a quartic with at most 7 nodes, a quartic with n at most 7 nodes. Then the conclusion is this variety is not stably rational. Then X tilde is not stably rational. Just let me make a remark. Well, the remark is that when we have 7 nodes, then previously, before her work, it was not even known that such a variety was rational or not. Okay, where open to know even if X tilde was non-rational. Okay, so here I will just just to give an idea, because I will do it in more details in the following example. Okay. So idea is specialize to RT Mumford, then show that RT Mumford example has no decomposition of diagonal. And here the singularities turn out to be important. The fact that uses that RT Mumford variety has only double point singularities, only ordinary double point singularities. And then use proposition 6, which was a proposition about behavior in the family of if you have one bad point when you have non-integral decomposition, then it's also the case for a general member. So let me keep it like this for the moment, and let me explain more in details in the case of quartics. So here is the next example. Sorry. So in the next one, I will do the specialization argument in detail. So the second one is enjoy talk with polyethylene. And so this is about quartics in P4. So quartics of dimension 3. Okay. So let me produce a general family of these quartics. So the coefficients of the quartic are parameterized by a projective space, right? You just have some coefficients to pick. So let me denote by P, like this, the projective space. So an exercise to compute the dimension that I don't know how to do. So projective space of coefficients of quartics in this projective space of dimension 4. And now we have a family X over P. To a point you associate corresponding quartic, be the family of quartics. Okay. So in this family, we are interested in the locus of quartic, which are not stably rational. So that was the question. So let me put, I decided to put n, like non-stably rational, in P, be the locus of just this set. Okay, be the set, be the set of points B, say complex points, such that the corresponding quartic is not stably rational. Okay. So here is the theorem. So first, N is the risky dense. So we have lots of points in the corresponding to the space of coefficients such that the corresponding quartic is not stably rational. Then N contains a point over Q bar. This is thanks to the help of Olivier. And also a very general point also is in N. General point B of P is in N. And I should also remark that here we have a produce a point over Q bar by thanks to the argument of Tatara. One also has points over Q actually. Okay. So remark, so by the work of Tatara, so remark 3 of Tatara, N of Q is non-empty, so one and also have a point, has a point over Q. Okay. So let's prove this. So who will give me a quartic which is supposed to be close to the examples that you just see? So let's consider A or Z, I don't know, a singular quartic. So we have this, we have this double cover, which is a variety of Artin-Mumford, which is ramified along the quartic. So let me write it again. So I write it like this, double cover plus these coefficients. Sorry, it takes some time. And during the time I write it down, you can think, what could we do to produce a quartic starting from this? Some people know answer. Some others are sleeping. So there is only one coefficient here, which is not of degree 4. And the first guess would be just multiply here by the 0 square. This gives you a quartic, which I will call Y. So what can we say about this Y? So first, being easy could be helpful because this variety is birational to Artin-Mumford. Precisely because we put here just this 0. Okay? Birational to Artin-Mumford. Just take an open Z0 equals to 1. I mean, here the coordinates are homogeneous, so it corresponds to Z0 and non-zero. So once you put this, you realize that actually it is precisely the same one as an open for Artin-Mumford example. Okay? Okay. Let's now look at singularities. So I will write it down. So it's slightly more complicated just rather than double point singularities. That's why we needed to care here about this notion of CHD or trivial map. So singularities. So the biggest problem is a line, which I call L, and which is given by equation Z0 equals to Z1 equals to Z2 equals to 0. So this is all these points are singular. And so plus, I mean, we have these singularities and other easy singularities, which are just ordinary double point. Okay, so well, let's just try to blow up the line. So let P be a map, which is just obtained by blowing up the line. Be the blow up of L. Well, unfortunately, this is not the end, because y prime is again singular, at, again, a line, L prime, which is the p minus 1 of a point P, where P is a point of the line with coefficient Z3, with the coordinate Z3 equals to 0. Okay, so, well, we persist and blow up the second line. So, 3. Now, this one is a blow up of L prime. And now we are lucky because we have no more singularities, but these ordinary double points. So, and finally, Z over Y double prime is the blow up of ordinary of, actually there are 9 ordinary double points. Okay. So we let F be the composite map from the resolution to the original variety Y. So what can we say here? So the conclusion is, so first, well, we understood that that is smooth. And then this Z is also a birational model of Artin-Mumford example. It's a smooth variety birational to Artin-Mumford. And so it has non-trivial torsion here. Z, because this is a birational invariance. This is torsion in H3, and this one is birational to Artin-Mumford. So hopefully we have nothing to do here. The invariant is have been already computed. Okay, and also, what are exceptional divisors? So this was the reason why I wrote the resolution explicitly. So exceptional divisors of F, are here. The last step, we have 9 of them. They are just quartic, smooth quartic with a point. Smooth quartic with a point. Well, anyway, we always see. Then we also have so these ones, and also the 10th one, which is a union of 2, such that the image of the second one is just P, this point which I denoted here, and it's a rational surface. Sorry. And the second one is fibered over the line. And this one has a generic fiber. So the generic, sorry, this is the generic fiber, a conic with a point. And it's also smooth. This one is smooth. And the conic is also smooth. So all this just tells you that actually this map is universally CH0 trivial because of the condition of the fibers, because of the criterion I just gave last time. All these fibers are very easy, so they are rational and they have points. And so conclusion is that F is universally CH0 trivial. Okay. Well, now we can prove the theorem 2. So maybe I will go there. Just remember that I called this quartic Y. Okay. So proof of theorem 2. So let me, by pedagogical reason, call B0 the point of P corresponding to this Y. Y is a quartic, so it gives you some point of the parameterizing space. Okay, P be a point, be the point, sorry, corresponding to Y. So remember, this projective space parameterizes the coefficients of quartics. And actually, by the description I gave you of the example of Artin-Marford, you just had to choose some conic, some elliptic curves, etc. So this is actually defined over Q bar. So note that B0 is over defined over Q bar. Okay. So now I can erase because we don't need the precise equation anymore. So let me prove the first statement about the risky density. So I will make a picture. So this is a projective space. This is our point. No, I will write it here. B0, which is defined over Q bar. Now let me take a line, L, such that line is also defined over Q bar, and which contains B. Now let me take the generic point of this line. Okay? And so here I will take the discrete relation ring, which will be the local ring of the L at this point. Okay? And now to this local ring, you can apply the proposition 4. So here is a proposition 4. It's still here. So you have something over a discrete relation ring. And if the generic fiber had a resolution which were universally CH0 trivial, and then, well, I don't know, here, for instance, and if you had this, so you have here Y corresponds to the point B0, so it corresponds to the variety birational to Artin-Marford. Here, the way we construct it here, this map is universally CH0 trivial. So we can really apply this point, this proposition, which tells you that, so, well, we may also assume that actually the quartic corresponding to the generic point is smooth because there are lots of them, right? So we just take a line which is not inside. So So proposition 4 tells you that if X eta is smooth, then it gives a non-CH0 universally trivial quartic. So non-stable Russian. And then, because we can compare this generic fiber with many of fibers, we can also say the following. So similarly, so same conclusion. For any x b, for b a point of the line, but which is not defined over Q bar, which has at least one transcendental parameter in order to be compared as in proposition, which I called 7 last time, which to the generic fiber. Okay, so here you see lots of points, and in particular, so you have this Zariski density. Okay. So let me first prove the third one. So the third one was about this very general point. Okay. So here, what we will apply this last proposition, which tells you if you have a fibration of an integral base, and if you find one point with the fiber having no integral Chow decomposition, then it holds also for a very general one. Now, because of the first part, we produced actually lots of smooth fibers which have no integral decomposition, right? So in proposition 6, B0 in P such that XB0 is smooth and has no integral Chow decomposition exists. So we have that the same conclusion for the generic fiber, so for the very general fiber. Okay, for 3. Okay. Well, finally, the examples over Q bar. So what we constructed here, we constructed we have Z over Y. So we said that this was defined over Q bar, so one can also find the coefficients in some number field. Okay, is defined over K number field. So there is some coherence with previous lecture. At least I pronounced number field once. Okay. Okay, and so this construction is over K, but we can also extend it over some over the ring of integers of K, and over some open, we will have the same properties of the fibers. So over U, which is an open in the ring of integers, we can arrange so that we have the following properties. We have that for any S in U, so first, over so for if we consider an algebraic closure like this, so sorry, over okay, I'll write it here. We have the family Z over Y and over U, such that for any S in U, the fibers. Let me write it a bit better. So Z, the geometric fibers over these finite fields, I mean, for an algebraic closure, will have the following properties. So it will have the same structure as before. So as the map is CH0 universally trivial. And because of the properties of the Étale cohomology groups, here we will have the H3 with ZS of Z2 and with two primary torsion is non-zero. This is also just obtained by the base change from the generic fiber here. So conclusion also, this variety, this ZS, is not CH0 universally trivial. So we can apply proposition which was about local specialization 4, which will tell that as soon as you take a variety which is defined over a number field, which is specializes to Z, even to Y, and which is smooth, you will have an example of something which is not stably rational. So let me write it here. So if X a quartic, define it over a number field, over Q bar or over a number field. And maybe I just finish writing here. And X specializes to YS, then X Q bar is not CH0 universally trivial, so non-stable rational. So I wrote smooth quartic, a smooth quartic. So this gives you a complete example of an application of these methods to this case. So let me give you some more examples. So in particular, I will continue with the examples of Tataro with many hypersurfaces. And this will be, this uses the second examples with non-trivial invariants, which uses ramified curves. Okay, so what was this? So 5.3 hypersurfaces. So many more examples of such varieties. So the result is the following one. So consider a hypersurface in Pn+1 with complex coefficients, very general. With the following condition of degree m, which is at least this one, 2 times what I wrote before. Okay, and here let's take n at least 3. Well, the conclusion is that a very general such hypersurface is not stably rational again. Okay, then XM is not stably rational. So in particular, you see that if you take example, let's compute something here. So you can take n equals to 3 or n equals to 4. So what it gives you? This will be, so we have m, the degree, should be at least this, right? 2 times this one. I'll write it again. So I guess we have 4 interesting cases, 4 here and 4 and 5 here. Not like this. Okay. So in particular, we'll recover again the examples of quartics. And also, his method allows to produce the examples really over Q, not over Q bar. Okay. So how the proof goes. So let me show you the case, which is the easiest one, when m is actually even. So this time we consider the following bed variety. So y over spec k with k algebraically closed of characteristic 2. It is a double cover, as in one of the propositions, a double cover of the hypersurface j equals to 0 with degree of j equals to d. And the double cover is defined by y squared equals to f with f of degree 2d. And such that, so these are examples by color, such that there is a resolution obtained just by blowing up the ordinary double points, such that a resolution with non-trivial H0 for differential forms. Okay? So this is provided by the proposition 8, I guess. And so now let's construct something which is interesting, which will be which degenerates to this variety. Okay. Okay. So we may assume that we are in the following situation. That actually all the things in characteristic 2 are obtained by reduction of something in characteristic 0. So we may assume that there exists a discrete Fodosian ring, fraction fields, with residue field little k, and with field of fractions big K of characteristic 0. And also we may assume that f and j are reductions modulo the uniformizing parameter little t, the uniformizing parameter. So it turns out little t of the polynomials of the same degree, polynomials with coefficients in A with the same degree. Here we have D, no, 2D, and here we have D. Okay. Now we are almost here. Let me define X. I will apply again this proposition here. Let me define X over spec K. The following complete intersection. The variety, which is defined by 2 equations. Y square equals to big F, and Ty equals to J. So I guess that you can find all this construction already in the book of Color. So what happens here? So for the generic fiber, so you look, so it's kind of a strange equation because for the generic fiber, T is invertible, right? So you get G So we have to G minus T square F square, right, equals to 0. No, the converse. F minus T squared G squared equals to 0, right? Now, no, it's okay, because, no, we mean T square F, okay. Okay, finally, okay. It's normal. After 3 times, one should usually succeed. Okay, so anyway, this gives you what? A hypersurface of degree 2D, okay? So hypersurface of degree 2D. And what happens for the special fiber? But for the special fiber, you will have a variety Y, because it's precisely the double cover of the variety Y, of this hypersurface. Okay. And the special fiber is Y, the double cover. And then I think that I will just say that using the proposition 4, similarly, plus the fact that Z here, so this here, plus the fact that V is not CH0 universally trivial. So unfortunately, I don't remember the number of the proposition which says that for universally trivial variety, one can have no differential forms. Okay, by this reason, it's the case. So it gives this here. Similarly as before. So one can probably also apply 6 to get for a general point, etc. So I think I will not give you more details here, but just tell you that if M is odd, then use degeneration to 2x union H, where X is a hypersurface of degree, X hypersurface of degree 2D, and H a hyperplane. And here one probably needs the proposition about the fibers which are not necessarily integral. So the one I gave last time. And it's actually, well, it's quite tricky, this part. So there is still some work to be done here. So I think that, well, I will stop lectures here. And because, I feel like I'd like also to give some challenge. So the challenge is the following one. Cubics in P4. So the question is understand stable rationality. So they are not rational because of the argument of Clemens and Griffiths, but the stable rationality is still open. So that's it. Thank you very much.